Hello, we will start the first lecture on Indian space program and its benefits. Uh, in this slide, you are seeing the dimensions of Indian space program. You have got the space infrastructure. We have been very much keen on having complete independence in making all these components possible. The first component is the launch vehicle. So, as you all know, we have got an excellent infrastructure facility built for having our own programs of launching. So, it comprises of launch vehicle development as well as spacecrafts, the cameras and sensors which are taking to either low Earth orbit or geostationary Earth orbits as well as beyond. That is the planetary missions. All the sensors are being developed there. The aircrafts, which are the spacecrafts, which are taking them, and also the sensors which are built within that. So all comprises the first part of the space infrastructure, followed by once you launch the satellites, what you need is a very strong ground segment which will do the data processing, collection of data as well as validation. The satellite data needs very strong validation program. So that's why we have got calibration and validation exercise also as a part of the ground segment. Then we also have ground stations connected to this like automatic weather station as well as deep space network, and also communicating to the spacecrafts which are flying above our head about 700 kilometers. So we need what is called telemetry and teletracking communication network, TTC. So this all comprise the ground segment. Yes, data sets are available, processed, all validated. Now it should also be used for the real applications. We have a very strong research program as well as national projects applications are there, where we are looking into the national resources requirements for managing the natural resources of the country, which includes also the meteorological and ocean studies, satellite communication and navigation programs, as well as disaster management support and so on. So the applications are the ones which drive the programs of the above two. The applications drive what is required for the sensors, and when with the sensors, the eyes, what they call it, eye in the sky, the sensors which are going to be triggering the ground segment requirements also. But once it is all done, we also need capacity building, and that's why today you are here with us mainly to make this technology usable as well as possible to apply for various requirements. We need people who can understand the technology, get them trained, and so on. So for that, we have very strong institutions which are built for giving a strong education program. Like we have got Indian Institute of Remote Sensing, as well as for Asia Pacific we have got the Center for Space Science and Technology Education. Then also for many governmental as well as private people who are already working in some companies, the hands-on experience training from the very experienced the scientists in Space Application Center, NRS as well as IIRS, all being given to them for training or providing them how to use the satellite data for their applications. Then we also have a full-fledged Space Science and Technology Institute. It's one of the kind in our region, so we have that as well. Then we have other programs which are purely based upon national resources natural resources management system, wherein we are connected to various government organizations including ministries, urban ministry, as well as we have the agricultural ministry, all which are related to the national resources requirements, all will be connected through a system, and that is what NNRMS means. So through NNRMS we are fully connected to various departments, and we take their inputs, what they want, and build accordingly all these above components which I already told you. And also we are going in for various countries, other parties who want to receive our data as well as get benefited out of it, for which we have got Antrix, which do all the planning and programming. And we also have international cooperation. As you know, many of our launch vehicles, I'll also be telling about it, that we have many satellites for foreign countries we have launched through bilateral as well as multilateral cooperation with various countries as well as organizations. As you all know, many of you would be quite aware, the Chandrayaan-1 mission, we have got more than 50% sensors are built by the foreign laboratories where the very important science had been reported. Coming to the space infrastructure, we have started with the satellite launch vehicle. Of course, this is a very beginning of our space program. As you can see, the period 1979 to 83. It was a very testing time for all ISRO because the failures have been phenomenal. Many a times we are learning from ourselves by our mistakes, and this is how we have gone. Then we have gone into augmented satellite launch vehicle, wherein we have from first level we have gone to a larger lift off weight, the weight which the rocket has to take from the gravity force. As you can see here, from 17 tons, we have gone almost to 39 tons, more than double. We were able to achieve it, and all that to mainly support the payload. Payload really means here the sensors which are going to image and process and send you the data. That was only 40 kg, which means you can do only mini satellites had been jumped into 150 kg. So this required a very huge augmentation, and that we did it with the 5-stage solid state propellant, and it was partly very successful. Then with all this, the lessons learned, wherever the mistakes we have happened, happened in our launch vehicles. The launch vehicle transportation is not a simple job. Failures are part and parcel of this. And with all this learning, we have got into a stage called Polar Satellite Launch Vehicle. As you know, this you can see from the first level when we started, it was 17 ton. Now it is about 295 tons of the lift-off weight, and you can see the kg of the payload capabilities. From 40 kg it can go up to 1600 kg. So this is the phenomenal jump which had happened, and in fact, as you know, PSLV had become the workhorse for ISRO for launching several satellites. In fact, the recent ones you may be knowing, at a time we had sent about 20 odd sensor satellites launched at a time, which itself is one of the important milestones which we have achieved. Then also we have GSLV, geostationary. Up to this is about within the external forces. That means we are about 680 to 700 kilometer orbit height. But come to GSLV, when you are going to geostationary satellite launch vehicle, which is about 36,000 kilometers away from the Earth's surface. This orbit, why we have to go? Unless you go to this, you will not be in the same position as the Earth moves. That means the satellite as well as Earth rotations are all almost synchronous, so that you are seeing the same object, or in this case, let us say Indian subcontinent region, continuously throughout its lifetime. So this is how we are trying to focus a particular region and collect as many information as possible. For example, when you want to monitor a cyclone progress of the cyclone, you need to monitor every 15 minutes. So it is all possible when satellite is not moving with the Earth. So it has to synchronize with the Earth rotation. And that is what GSLV really means, and that's why we have to go to 36,000 kilometers. And as you can see here, again the weight is going from somewhere to 414 tons, because you have to take this vehicle far away, so naturally the fuel requirements are going to be phenomenal. So this is the overall first space infrastructure which we have built, and as you can see here, we made first history. Particularly the launch vehicles of PSLV had not been very problematic, because we have started with SLV and we have been successful at some point of time. But coming to GSLV, it has been a very long failure. In fact, it is almost 20 years of very strong effort which had been made, and the history was made on 5th January 2014, where we had very successfully launched indigenously developed cryo upper stage, which could be required for launching this particular satellite. And it is a very proud moment, because this is where we started that without the support of foreign countries, we ourselves can go and build this. And subsequently, again, the last 2 years we have been launching one or other on this GSLV to show that it is not just an accident by which we are successful. We are now fully known the technology completely to follow it and do it. And as the word in the box says, the space transportation systems are unforgiving. That means you have to be like it's just like how a doctor does a very complex operation. If he makes a mistake, yes, the patient is dead. The same is the case in the space transportation. If you make a very small error, maybe a small millisecond error in your software, which have to do various activities, yes, the failure will be instantaneous. Even you have spent 4 years, 5 years on this, it doesn't going to help. That 1 second, milliseconds become very crucial for the mission, for the success. So that's why we say the line between success and failure is just thin. If you with all this, if you are meeting it, yes, you are successful. Otherwise, no. All your effort comes to naught within few fraction of the seconds. So this is where the space transportation becomes very, very critical, where we need to be extremely careful, and the quality assurance. This is a very important part of the space transportation. The quality assurance of each and every component, whether it is hardware or whether it is software, it has to be completely in sync, and it should be 100% possible for taking a very successful launch. As you all know, some of you, or maybe this is just want to say that ISRO had made a very significant progress in planetary, that is beyond our Earth. When we had a very successful first planetary mission to the moon, our nearest moon we have, that we go to that point, and we had very successful launch. As you know, this launch was also very important scientifically in that it provided that there is a possibility of water molecules there. So that was the biggest contributions from this mission. And for us, that ISRO can launch a satellite beyond our Earth was achieved. So for technologically, it is a big success for us, and also scientifically, it's a very important mission for the entire globe to understand what is the scientific phenomenon which have been not answered for several years of the human quest on moon. Then we also had a very important another mission, which is interplanetary mission, where we had Mars. We are able to reach by November 2013. From then we had a lot of scientific outcome from this particular study, and moreover, it's the first technological achievement of the mission that we are able to launch as per plan without much support from outside. It's in a very dedicated way by our own understanding of all this orbit and the platform understanding of the system. So these two are really the milestones in ISRO's program so far. And also, as you can see, it also requires a ground segment. I'm coming from space segment. Now you see, look at the ground segment requirement. As the satellite, the spacecraft taking these to planetary missions, so we are crossing a level wherein the local network of satellite, the tracking centers cannot do it. As you can see here in this particular slide, all this the orange color ones, all the satellite or the networking stations which provide you control on spacecrafts, where the rocket is going, where this information coming. In fact, many of you would have noticed when the satellite is launched in the launch day, the satellite, where the rocket is going, what are the stages happening, it has been communicated to us, and you would have seen in screen which stage what is happening. All this is possible because of this networking system, networks of antennae which communicate to the satellite, to the spacecraft, as well as also take the return signal from there. Okay, but then when you go for planetary missions that is beyond 1 lakh kilometers, these networks all will fail. It means you will not be able to electromagnetically contact the spacecraft by that. So you require a larger dimension. That means you need a very separate system which is called deep space network. In fact, in the whole of world, as of today, we have got 4 such ones. In fact, IS Indian Deep Space Network, it just formulated before the launch of Chandrayaan-1, and now this is one of the frontier networking station, which is also supporting various international programs today. This is one of them. I'm showing you an antenna. Whenever there is a possibility for you to visit this ISS DC Bailalu, which is near to Bangalore, you can see this antenna fully developed by Indian support. We can see the 32-meter indigenously developed antenna was fabricated and made possible before the launch of Chandrayaan-1. So parallelly, along with the spacecrafts, we also were planning for the ground segment. So this is a total plan which is required. As you can see in the next slide, how this whole plan has happened. You can see here we have got Mission Operation Center MOX. We also have the control system. Then we have got ISSDC. It is an Indian Space Science Data Center from which all scientists, academia can take take the data sets from the ISRO free of cost. You just have to register yourself, take the available analysis and studies. And this is the entire platform by which we have made the ground segment for the space program, particularly related to planetary as well as beyond our Earth region. So the evaluation of our program has been very strong. 27 years we have been crossing. Now IRS 1A, 1B we started somewhere in 1988. Now we are into newer satellites and programs, and we have, as you can see here, we started in the beginning. The bottom box tell you how we have progressively improved. We started with the helicopter images, then we had our Landsat mission stations built, started using the Landsat data, then we had the Bhaskara utilization, then we had joint experiments program with various teams. In fact, US was first participating and making available the television applications of this program. And we also have many other support which have been going, and now we have thematic based satellite series like AutoSat. One I'll come to one after other later. OceanSat, as the name says, some of these sensors are specifically built for ocean applications. Some of these satellites are built specifically for CartoSat, means basically for mapping applications and so on. There are plenty, and that's how this from the simple vision of imaging Earth, we have gone into theme, which is now currently the very important area of research. Now, as you can see, I'm just giving a gamut of various satellites, sensors which are developed, imaging systems. As you can see here, the Bhaskara 1979 to various other cameras which have been built, and we have all these ocean applications and so on. There are plenty of them, and you can see at the bottom, which is more important, from sensors which are capable to image less than a meter to now 1 kilometer and above can also be collected at a time. So this is an advantage where different resolutions, different wavelengths, all can be collected in a program in our for applications requirements. Again, here I am giving you much more breakup. As you can see here, land and water, we have got sensors like ResourceSat 1 and 2, which is already operations. Then RISat 1, which is actually a radar imaging satellite, which is also first of its type in India. We have developed it, and it is giving excellent new products and services. Particularly RISat 1 will help us in seeing through clouds. That means whatever all weather conditions, we are able to image and provide the information. Then high resolution data, we have got Cartosats missions which are providing you very high quality data for spatial mapping, where you can go for very high resolution imagery like 0.8 meter panchromatic and 2.5 meter. Basically, it's a stereo imaging. That means you are able to generate the digital elevation models. And there are ocean applications. We have got OceanSat 2, where we have got ocean color monitor, scatterometer analysis for the sea surface information, and also weather and climate, where they are more of geostationary in nature, and keeping it at one particular place, you can repeatedly collect information about what is happening in the Indian subcontinent. So the primary criteria for our Earth observation plans are: we want to ensure the data continuity for operations purpose. That means it is not an occasional collection of data. We are providing the data for all the users in a continuous basis, so that They can use this data for various applications. For example, if I want to know what is the river inundation which is happening in some parts of the country today, there's a lot of floods which are happening. How much area has been affected by the flood can all be managed because the data sets are continuously available for users to know what was the previous year and today what is happening. And we are also having a lot of improvements because user feedback is very crucial in this, and we also have user meets very regularly conducted and take their inputs, as well as I told you, NNRMS is another platform where we have the ministerial contacts so that their applications are all taken into account. And empowering the Asia and Pacific, we don't just stop with only doing within our nations. We are also developing all the countries which are demanding, which are needing such support from us, Asia and Pacific regions, where we are also telling or training them to do remote sensing and GIS through our STEEP program, and also small satellite missions. How they can build a small satellite for their own requirements is also being taught. Then we also have SARC satellite and satellite communication programs for telecommunication, tele-education, as well as disaster support. So this is some of the how the missions are spread and how they are using for various applications. Now I'm giving you specific applications. As you can see here, agriculture is one of the important uses of satellite data because you can monitor the Earth surface very regularly and try to get to know what is happening. And you can see already they are in color. I will come back how these color information are very useful to you. And similarly, fisheries. See, the fishermen, when they go to the field to go to the sea to go for a fish catch, so ocean is ocean. The word itself is ocean. That means they should be very clearly directed so that they go to the spot where the fish catch can be maximum, and they can utilize the fish catch with a very appropriate way with a minimal fuel cost. So that is how what is important. So that again, there are satellites and sensors developed exclusively for studying this because fishes all live based on some plants which are available. They live on that. So those plants can be mapped by the satellite, and that's how we are able to do that. Then we have watershed, again how the waters are drained, where is the source of conservation of water is possible. All that will be studied by watershed management system. Then also we have got irrigation, again similar connected to that, where there are potential of water, groundwater resources, all need to be studied. Then national natural resources census, like any other census, how is the potential of the land today compared to last 5 years? How the land is fertile even now? What is the wetland status? What is the degradation status? How much snow is gone? How the vegetation patterns have changed? This is all some study where we do a periodic inventory of resources. So this is again an important application for nations. And there are other applications like forestry. Yes, the deforestation regularly happens, so we need to understand. And also we need to know the forest fire, how frequently it is happening. There are many recent cases of forest fire where they have to be monitored, how much area has been affected, all that need to be studied. Then snow and glaciers, yes, because of the global warming and various other reasons, what is the status of the glaciers from for the past 10 years. If you want to study and analyze, you need satellite data because it has to be covered for a larger area and understand this part of it. And because the snow and glaciers have got direct impact on climate change as well. The national urban and information system, as you know, the population is growing, the demands of people going from rural to urban cities cannot be stopped. So we should also then know what is the infrastructure available, what is the urban requirements, as well as how the e-governance, how people without moving on the roads can do the business from sitting. Like today we have got many such apps which help you to get what you want sitting in your office or home. And the decentralized planning, of course, panchayats, what is the main assets of the panchayat? At local level, what are the information available need to be mapped. That again is taken in a very big project way by ISRO. Then we have weather and climate. Of course, many of these parameters The central satellite data satellites have been built as per the needs of the Indian Meteorological Department, and all these important parameters like ocean state forecast, sea surface temperature, sea surface heights, as well as heat wave predictions. All are part of predicting the weather and the climate changes. So these are all whatever possible from satellite based approaches are provided through satellite platform. And once you develop all these products, how to make it available to the people, ultimately the people who are going to use it. So we have got many portals which support this activity, and they are mostly visualization, because mostly it is for analysis part what is happening. So it is more of visual insights, and of course in many places the data sets can also be downloaded. So we have got an NNRMS portal, we have got Bhuvan portal, as well as MOSDEC, more concentrating on the marine and atmospheric ocean and atmospheric sciences. Then we also have India India Water Resources Information System, which is WARIS, is again an important source where the lot of the big exercise taken care by ISRO in combined with the water the central water commissions, all were put into a website so that they know what is the potential of the ground water today as of what is available. And forest fire, I have already told you how important it is to monitor the some of the regions which are very prone for fire. It's not forest fire happens everywhere, but there are places where the forest fires are regularly happening. So it is required to monitor whether some catchy things are happening particularly in the months of summer, where the temperature is very hot, as well as the precipitation part is helping for fire catch to happen. Then the decision support systems, we have many of these parameters which can help for making the support. Of course, it is partly shared with the state government departments. Then we have got biodiversity information system, wherein you have got not only the forest cover, but also what are the species available, their status, all this information is available. And ISRO portal, of course, giving you overall what are the data sets made available for the public to take it forward. Of course, we call the gateway for Indian Earth Observation Data Products and Services. This is Bhuvan web page. Maybe many of you should visit. We have all data available for visualization, data archive, thematic services, as well as geoprocessing is also possible, wherein you can have online shapefile creation, terrain mapping, profile is possible. Then ocean services are there, web services, all whatever possible derivable from the satellite. And also our own research has also been made available for public to make use of this, and public also involves many academia. In fact, academia's role in this is phenomenal, as we see that many products and data sets are taken for further analysis. It's again another glimpse of one. You can see here Bhuvan India, as well as a whole wherever available. You have got the 2D mapping, 3D mapping of the regions can be seen. We have also open data archive where we can download quite a number of data for your research. In fact, I would like to tell you, I had seen many of students who are coming out these days from the universities. They do a lot of project with our data sets. Where they get the data? Mostly from this website, NRC website. We have also climate and environment products, which are very special applications, are also being done. Then we have thematic services, disaster, ocean services. I think some of it I already touched. And bottom one, you can see here, there are some specific portals for states. For example, state portal for Andhra Pradesh, Arunachal Pradesh, Assam. Of course, there are many. Just to show you only 3, I am showing you here. And also, it also supports the tourism as well as e-governance, water mapping, urban, and so on. So there are many components, not only for science application, but for other users also. A lot of information is made available for people. And of course, this I have already covered, but more or less you can see here there are many important science products, land science products. We have got ocean science products, cryo science products are also available. and atmospheric sensors. So it is a input for researchers because we got a lot of data sets available for taking it up and then doing it. Of course, data visualization, spot your satellite, where the satellite today we have got so many satellites launched by ISRO, where they are at now. For example, at 5 o'clock, you want to know where the satellites, which part of the globe it is, you will be able to know. India now, that means whatever satellite data collected today, you can visualize it and also fly on. So many such services are provided for benefit of people. And of course, why we all do that? Ultimately, it is one of the important criteria that United Nations have put, that all the observation systems of Earth should be made use of for societal benefits, which otherwise it is not a technology. They are very, very clear that any technology which can serve the people should be made for this purpose. So the Global Earth Observation System, have made already a good number of applications. As you can see, 9 important areas have been identified. This is where the more focus of research is also happening entire globe, particularly from the remote sensing community. But what is the advantage of imaging? As you can see here, when you go from the ground, where your observation will be limited to a very small size, then it can go up to, as you go up from 1 meter height to 36,000 kilometers, you can see how the scale is enlarging. So from 4 kilometers to almost 2,000 kilometers at a stage you will be able to cover, and that is a big advantage of covering. And why we have to collect it different levels, I think you will shortly get that answer to that, because there are certain applications which require local information very seriously for understanding some of the phenomena, but there are other factors like, for example, movement of the cyclone or weather forecasting. It doesn't require a very high resolution, but should be monitored at a very high repetition time. That means I need more and more data for understanding how the cloud patterns are moving, whereas for mapping applications I need the finest resolution possible. So this is how the ground coverage, and this would go in a way. And this is overall program, how the whole put together all what are happening is given here. You need to understand the physical process first of all. See, images are collected, but how you understand what is to be done, what are the factors which imply the quality of the data, all should be understood. Then we have to program the data acquisition. Depending on, for example, if there is a disaster happening, your program has to be driven towards that rather than doing elsewhere. Then we also have reception and storage. Then sequence of pre-processing need to be done, and post-processing, as well as finally the information, the data should go into the user community. This is how the entire thing is planned. And of course, you can see here, this is how the process happened. You have got the world, which is actually a 3-dimensional. In fact, into time, if you can take, it's a 4-dimension. Then once you collect a scene, that means the image is captured. That means it has got in a 3-dimensional at a particular time. That means time is frozen for that. That means image is having a time stamp. But then the image is now only a 2-dimension. From 3D it becomes 2-dimensional. That's why scene becomes image. Then from image, with all this data processing, with a lot of data sets collected, we should be able to describe the image of this of the entire Earth at a particular time. Then from the image and multiple data sets available, you should be able to go to scene description. And from scene description, with many wavelengths and information available, you should be able to go to description of the world, and then only the forecasting effect will start. That means you should be able to monitor and follow up what is going to happen in the next 2 years or even 2 hours from now, that can be predicted. So this is a sequence of processes involved in remote sensing system. Of course, when you do that, when you are modeling the world, you should also be knowing that the data, because ultimately Earth observation data becomes the only means in many occasions. So how to use this data, how quality it is, all that is becoming a very important answer to be given. Then only the user community will use it with confidence. Otherwise, if you say that this is some data which is not properly calibrated or properly understood, then they will not go for it. So the ISO quality, the word itself speaks that quality is that whatever the input that is going, it should be fit for the purpose. It should meet the requirements of the purpose of the user requirements. Again, as you can see here, the raw data, yes, it is not the best quality you would get in the beginning. I will tell you why this is so. And we need to understand the inverse processing. That means from this raw data as well as the conditions available, you should map the what is the actual scenario could have been there. And from there, you should try to approximate the object. This is what is possible in any system. Nothing can be 100% as the true information. So we are trying to approximate. This is actually a scene data which is collected. This is how you understand the system. Then it goes through what is called quality assurance process. Once it is approved, yes, it goes to the users. If it is rejected, again it goes to the loop back that it should be going back to the inverse modeling to improve the system. Then only it will be applicable for the users. So it has got two components, particularly the quality assurance has got quality indicators and traceability. This is something we work with very hard to know how the system is in place, how the quality is ensured for the users. Now, I'll just come back to some cases why this problem is there. Why, like any other system, why the images are not quality best. As you can see here, the images are collected first from platform which are actually floating. It's just like how you have a handheld mobile cameras or even the digital cameras, but while you're taking photographs, if your hands are shaken, the objects are shaken, naturally what you get is a blurred image. You don't get a very proper image first place. But then you look at this satellite which is at about 605 kilometers above your Earth, and then it is being affected by various perturbations. Perturbations come from gravitational forces, its own orbital vibrations, all that. So all this create an image which is not directly usable. As one of the images shown at the bottom, you can see here the true image would have been like this, but what you get is some sort of a completely jagged picture what is shown here on the left side. So from this data, you need to make a meaningful data and make the product data what is shown on the top. So that is where the processing or understanding the inverse process becomes very, very critical. And I have already given you the sources which are creating this problem are atmospheric effects. As you know, the haze and other part cannot be avoided in your imaging because the imaging comes through the atmosphere. Then you have got sensors, very high resolution sensors have more and more other problems, and also orbit related effects which I have already told you. Yes, in the atmospheric case, as you can see here, although you would like to get the minimum actual signal, but you are also not only that, you are collecting signatures from the various scattering phenomena. So with all that, what you get is some sort of an image which is haze in nature. It is not purely the one which you would like to. You can always see a blue haze on the top of the image. That is basically due to the atmospheric scattering effect. So you need to understand the atmospheric process to completely process and bring back the original image which should have been if the atmosphere were not present. So this is one of the challenges where atmospheric sciences are becoming a part of the image processing activities of satellites. And you can see here, this is again optical system which is imaging your data. As you know, any system, there is a slight out of focus or any of such image problems, you get up into some sort of a blurred picture. This has always happened when you have very large optics in the system. Sometimes the focus cannot be exactly accurate, so slight blurring will be there. As one of the images shown at the bottom, you can see here the square bars and dots are not looking sharp. Again, that need to be understood. That means you should really model the optical processing also to process and recover or restore the original image which is shown at the right side here. So naturally the second one is more applicable for the users who want to know exact size of the objects than the first one. Then again you can see another image. Here it is not blurred, but it looks slightly dull because of that same effect of atmosphere or as well as a sensor problem, and that can be very well sharpened. And this is something called modulation transfer function, which actually when you go for higher and higher resolutions, because the detector size becoming very, very smaller, naturally the contrast transfer, the area available for the contrast to capture the signal become reduced, and that is why we call it as 15% compared to a larger image. For example, LIS3 has got about 24-meter ground resolution, whereas C1 has got only 2.5-meter resolution. So you can see here how the modulation transfer function also gets reduced, and that again gives me an image which is not too sharp for your analysis purpose. So you have to improve the contrast by understanding the system in a whole. Coming to the sensors, there are many issues can come from sensors. As you can see here on this, I'm sure you are able to see it very clearly. You have got odd even effect. That means two ports like a striping kind of pattern you can see here. That automatically comes from sensors of very high resolution, because odd and even ports of the CCD detectors are read separately, processed separately. So whatever small bias is there, which will come in the output, will be seen as like this, what is shown here, and that needs to be processed. Similarly, there can be, because multiple optics are used, there can be sometimes ghosting. As you can see here, there are some ghost reflections are possible that need to be corrected, and there are compression related issues are also there. So there are many issues which are need to be understood completely if you really want to make use of the system data which is more reliable. And geometric effects, as you can see here, it is not really spoiling any of the radiometry, but it is only disturb the geometry of the objects. That means the line gets curved, or the features are totally dancing, as you can see here, in a very curved way. As the flight takes the image, what you get is like this. Maybe a little more clarity you will get here. See, this is the original object. Sorry, true object is on the right side. The distorted image can be like this: a circle, a clean circle can become an oblate, a spheroid kind of thing. Then a straight linear line can be curved. A square can become rectangle, as well as equi-spaced squares can be compressed in some point and expanded in another point. So all are possible in a geometric sense. And this example maybe because, as already told by the organizer, that this all data will be available for you to go through again and understand. You can see here how, for example, depending on the flight direction, ideally I would like to go straight and image it, but because of the various reasons there will be a roll of the satellite. Then what happens is, you can see here the equal nice squares which are patterns were there, they gets compressed here. You can see here there the sizes are reduced, whereas this side is expanded. So this is for the positive direction. Suppose if same thing happens in the negative, the other side will get expanded and this gets compression. Similarly for pitch, that means going up and down the nose, it will again create compression in one side, on the other side it will be expanded. And also skew when you go for both the directions, yaw. So the roll pitch yaw are some of the attitude parameters which really affect the quality of the data. And of course, earth curvature by itself create one other issue, that as you can see here, the two objects A and B, as well as X and Y, on ground they are very different, but because the three-dimensional image is surface is mapped onto two-dimension, they appear as equal. So that is where your knowledge of exactly what position I am imaging is very critical. So these are all parameters which go into the model, so that you are compensating the earth curvature when you take the data sets. And of course, this is some simple example of corrections. You can see here nice banding which were there in the original image is completely restored for the user, so that they can use the data straight away. And you can see another type of error where there are some streaks, because this is where the scanning mirror, when they go from one end to other, the what we call it as the memory, it's not a zero memory detector. That means some spillover of the charges are also taking into the water side when the sensor is going. That's why you know this, you get the streaks in the dark sides. But every pixel has got this problem. Please understand, this is a phenomenon, even it is happening on the land side. So all were corrected, as you can see here from left to right image, the kind of quality enhancement which will tell you what is the offline correction we need to do for such an effort. And remote sensing, of course, it is not done in one panchromatic or something. You have got a multispectral image which is able to help you. For example, from this image, a thematic expert will tell you in future that red is a very good example of vegetation, whether it is cultivated or natural. For example, the thick ones, what you see on the top, the green spot is basically a forest kind of area. whereas the rest are all, the urban will be shown as some sort of a cyan color, whereas the same thing is shown in the bottom panchromatic image. But as you can see here, the trees are not identifiable so easily as what you can see in the multispectral data. But the advantage of the panchromatic data is you get more and more spatial structure. For example, I can see the buildings more clearly, tree tops more clearly, as well as the roads are very nicely found. Even the small roads can be identified. So each sensor has got its own importance and applications. So that is where we combine such users, combine their applications to generate much more meaningful application or the utility of the data. Then why we go for this one multispectral is, it will be very clear. As you can see here, there are many features on the earth which are having some signatures. So this is how we try to understand the sensor, understand the features through the signatures it has got from this one. As you can see in the simple schematic, which what is shown here, there is a dark object here in band number 1, but as it go to the kth band, it can become another signal, whereas there is a reverse is possible in the square. So each one is a particular kind of a object, so through which we are trying to discriminate the objects and also study their behavior. And this is another example which is shown here. As you can see here, there is one which is a yellow circle. It looks dark in green band, but goes to shortwave, it becomes very bright. This is a typical of vegetation as well as the regions where you can get very clear signature change, because vegetation gives you very bright at some point of place. Then you can see here, for example, of course, this is yeah, there is some green. This is some. This is not exactly the. This is actually a land use applications, right? Sorry, it's not vegetation. And you can see here the water body or the shallow waters. You can see here it was very bright because the blue reflections will be there. But as you go down to shortwave, they become darker and darker. Similarly, when you go to reflective bands, you are not able to see some feature which can be seen in thermal band. So this is how the signatures are available for you to analyze and use the satellite data. And of course, it comes into statistics. They are not single pixel, so you have a group of pixels, and that is how the multi-band will help you. For example, if I use only one band, for example, band 4, the DN numbers or the signal from barren and crop will be identical, but by using the other band, you are able to separate these two very easily. So this is how the multi-band concept becomes very critical for analysis. And of course, from multi-band, now we are also having sensors which make a continuous signal. So earlier you have got 5 bands, you have got 5 points for the Earth object, but now these bands are going into 200 as well as to 500 channels are available these days. So you are able to make a continuum of this spectrum rather than single at some locations you get the information. And LIDAR is another important application by which you, by light detection and ranging, you are able to find out the vertical variations. And of course, you can see here one of the important applications is one bridge which is totally invisible in the left side image. You are able to make here as a finest reflection possible. So the height variation can also provide through LIDAR very new applications for you. And of course, the Earth observation image analysis is one of the most complex systems in the Earth, because as you know, the features are so many to be separated, and each one has got its own groups. For example, clouds, when you want to study, you need to know what is the cloud density, formation of the clouds as well as shadows. Then surface water will have liquid water, snow, ice, and so on. Every feature has got its own subclasses. So our job is to find out ways and means of separating this from the other as well as within the classes. So this is a challenge for the image processing, image classification application scientists. And remote sensing today are not available only from one, but it is also available from multiple platforms. As many of you would have heard, this drones becoming more and more popular, and they are now able to capture the images for events as well as very specific application like disaster. It can be very handy for understanding the scenario. And some of these applications go on human scale. remote sensing applications can be also separated into two ways, like human scale. That means I am trying to observe the objects at human scale observation. As you can see here, the Barack Obama's inauguration, the ones what you see like flies, they are actually the heads of the people. So how many people have been assembled and how they are distributed can be very easily seen here. So these are actually very high resolution. That means they are to be very focusedly targeted and collect the information as required. Is another application of human scale. As you can see here, a very busy road of toll gate of a Delhi highway. You can see how many vehicles fly through the toll gate at a particular given time can be studied. So this will help you to plan and monitor, are there any, in case of any road blockage, how it can be managed, or even in a time when there is a traffic flow during vacation time, where this number also will go phenomenally high. How to manage this also will be an important point. So these are all working at the human scale level. But remote sensing also looks at regional scale. That means you are also looking at various other beings. That means, for example, how the ice breaks in the ice shelves of Arctic and Antarctic regions, for which you don't look for a very small like human scale. You need a very large scale and continuous monitoring of this. In fact, I think 2 days, just 2 days back, there was a very important article on how the ice is getting broken in various Antarctic other regions. So these are something we need to look at it and monitor it. As you can see here, each ice pieces have been identified with number and their floating time, as well as how much time it preserves. All will be very important to know about the climate and other parameters. And again, another event based ones, again it's a regional based. As you can see here, the volcano eruption happened in Alaska. In what direction this the dust has been carried out, all that need to be studied. So this requires a collection of data in a systematic manner and wide areas to be collected. So there are two aspects of remote sensing. One is very high resolution, focus on a small target and narrow field in imaging, whereas the other one is a low resolution but collecting a very larger level and then and collecting it very systematically in a regular fashion. So these are two sides of the remote sensing applications. And of course, resolutions are there. You can go from very finest resolution to a coarser resolution. As you can see here, how the pixel will get broken up. So this is a spatial resolution. I am sure the subsequent speakers later will be covering this more detailed. So I'll just skip on. And these are always some sort of important thing, that spatial and temporal resolution. When, as I told you, when you want to have a very targeted one, that means we require a very high resolution imaging, that then the recovery, when that satellite can come again, is another point. As you can see here, 1 meter data, sometimes it requires, ideally speaking, if it is collected, it can take even up to 2 to 3 years or 5 years. But then this is not the way. This is how it has been actually done without any maneuvering or something. Today, what we are doing is we are going for constellation of satellite. That means it's not one satellite, but a group of satellites, so that the revisits are increased many a times. And also, we are also equipped with high resolution sensors, satellites with a high agility in this platform, so that it can turn, rotate, all that, so that you are recapturing the images of the same area is more and more possible. And radiometric resolution is another important parameter which tells you how many bits per pixel I am recording it on this sensor. As you can see here, this is one which is 8-bit data. You have got the features, but then there are all like a black and white, or the levels of gray levels are very clear. So it is not giving full details of the same image. But you look at the second image, what is shown on the right side, the details of all the buildings, even the top gray variations, the ground features, all that come out very well here. And that is the advantage of high resolution, radiometric resolution data. In fact, this one image can tell you how 1 bit per pixel you are able to not see any object here in the image, but 2 pixels, some blacky things are there in the image. But as you go to 3 pixels per pixel, you see some structure like features, and as go from 4 to 8, the complete formation of the object, an aircraft, can be fully visualized and understood. So this is how the radiometry plays a very strong role in identifying the objects and make use of this for applications. And as you can see, one of the very excellent examples that you when you have the 11-bit radiometry such as Iconos and QuickBird, there are many satellites now providing this. You are able to even see the objects in the shadows. Okay, that is the advantage of high resolution, high radiometric resolution sensors. That means per bit, per pixel, I have got a large number of data sets. So smaller and smaller information available also can be picked up by that. So that is one of the advantages of 11-bit high radiometric resolution. Now, as I told you in the inaugural time itself, this all come into one very important technology: the global positioning system, GIS, as well as remote sensing, all put together what has now become geotechnology or geospatial technology, which helps for people to know where is what. That means today people have the question of where, what is happening at something. So that means people want to know where I have to build a house. From where, see today all of you would be using mobile for this application. Like from here I want to go to a place, how to go. So all this is what we call it as descriptive mapping to prescriptive means if it is happening, what is happening, what is so what. That means how the spatial relationship between one layer to the other are there for deriving or modeling. This is where the analysis comes into from mapping. So one is mapping, that is bringing the information into a mappable solution, but other one is to provide analysis from that kind of data sets available. So one is graphical, as very nicely put, graphical, the other one is numerical. This is the importance of this geospatial technology. And today geospatial technology, as I told you, will lead to a very huge roadmap for our Indian scenario. Now we have started with smart cities, and some of you would also heard about in recent times smart automobiles, which is coming up very well in a big way, where the geospatial technology is very strongly utilized, and Internet of Things, that is doing everything through internet, is also coming up very strong way. Defense applications are also very much connected to this. Today the persons who are in the field need to be connected and need to be guided where to go and what to do. All that will be done through geospatial technology, and disaster management is one of the biggest applications of geospatial technology, particularly for people who are in the who are affected and who are not knowing where to reach. And this is the way the geospatial technology has very strongly utilized for this public for this important application of requirements. We have many challenges. Why, see, if all are available already, we have nothing to do, but there are 2/3 of world is yet to be mapped. 2D, 3D city maps, road and utility networks are yet to be developed, and also integration of a disparate sources and applications. This is one of the very important topics. That means sensors and various data sets from various platforms are available. How are we going to use this and make meaning out of it? And all why we are doing it is when that large data coming from various platforms, various sensors, how you can connect it with the help of sensor webs, so that these data sets can be brought to a second level, and also further data fusion, where you are integrating many of these data sets to understand what is happening, and then finally for the users to know whether there is going to be a very heavy rainfall or not. So this information knowledge is only a few bits. Sometimes it may be just a 2-bit or 3-bit information. It's just yes or no. But then to generate this knowledge, you require petabytes and more the data sets to be driven for this. So the main idea of the whole Earth observation program is how to bring a synergy of all these models and methodologies to make the satellite data fit for the purpose. That means information should be made available without major policy hurdles, as well as without much of impact or the requirements from the user end. And that requires this kind of a very big data analysis. Of course, this is all future where this is going to happen, and I'm sure in course of your study you will be learning more and more about it. We have got the remote sensing source that becomes the baseline requirement of all this, from where most of the data comes in. Then we also have automatic processing, which is again to be built up, because otherwise the time delay will be there. User made errors also can be more, so that needs to be avoided. Then we have the information fusion, where the multi-source multi applications are connected so that you can get one unified information possible. Then smart databases, from all this data we can find out, you can do the mining and try to understand what could have happened though the data sets are not available and so on. Then you have got the human computer interface, analytical applications requirement, knowledge discovery and decision making. So when it goes from this, data volume will be very large, as you said, petabytes, and by the time you go to the knowledge, by using all this data finally to know what decision I have to take, that will be megabytes, sometimes kilobytes, even bytes. So this is where the data sets, a big data analytics become a very crucial challenge for all the academia. And Earth Observation Program 2025, we have got a very huge plan. I am sure this is not just a program just started and closes somewhere. You have got a huge series of satellites to come. So there are many benefits you all going to have it if you take up this particular subject as your main activities. And of course, there are many projects can be suggested. In fact, this is one thing I'm going to request all the coordinators to provide the many projects and support, and we can, as our IIRS has got faculty who can guide you in that. So certainly many projects can be suggested for students so that they all get familiarized with this Earth observation program and take up more projects through this. And why we do all that is the single most valuable product of all any of the space program is our Earth. How we understand the Earth, how we preserve the Earth, as well as monitor the Earth. So this is the single most product which every scientist, Earth observation scientist, application scientists all work on this. With this, I conclude my talk. Thank you very much.